Hello, my name is David Sims. I'm a graduate student at California State University Long Beach, and my major is Geographic Information Science. In the first video, I demonstrated how to use Python tools which I developed, and these tools help you use slope, derived from a DEM, to improve classification of Landsat imagery. The purpose of this video is to explain how the code works. So, of course, we begin by importing ArcPy. From ArcPy, Spatial Analyst, import everything. Check out the spatial extension. Set our environment setting here so we overwrite outputs. This way we can keep going through and testing the code without having to change the name of every output. And then prints a little message here. Then the first thing we need to do is start gathering up parameters and assigning them to variables. So we do this using raw inputs from the user so that this tool will be robust and reusable for different areas and with different files and so on. So the first thing we want to do is set our workspace here, and then it prints out, does your area of interest require you to mosaic DEMs together? And so this is going to work in conjunction with the if and else flow control statements. So if there's DEMs to mosaic together, it's going to follow this path through the if statement. And if there's none to mosaic together, it would skip down to else. So these two things are almost exactly the same. The only difference here is that the mosaic to new raster tool was removed from the top, and so I wrote this part of the code at the top first and basically cut and pasted it into the else and just made a few modifications. And therefore I will not describe the second half because it's pretty much a repeat. Once the user has given the input whether they're DEMs mosaic together or not, we're going to just say that they said yes, and we're going to follow the if statement here. So we're going to change the workspace to the unsupervised folder. If you recall, there's subfolders in the workspace to keep all the outputs organized. And then I have it print out all the rasters in the unsupervised folder using list rasters. I did this so not only could you see what's in the folder as you're running the tool, but also this will allow the user to cut and paste the name, because Landsat files can have really big names and so can the DEMs. So this would eliminate the chance of having a typo, because if you make a typo, the tool will error out when you're inputting these file names. So by doing this, it makes it really easy. And then here, I return it back to the original workspace. I just did this because it helps me stay organized, and probably because I was developing each section of the tool like individually, and so it just sort of helped me keep organized of what code I would need. Like here, when I set the unsupervised parameter, it's workspace plus the unsupervised folder. So here we set the unsupervised variable, so this would be the classified image. As I mentioned, this works for other classification methods besides unsupervised classification, but originally that's what the project was unsupervised classification when I first developed it. So then it prints that the projected coordinate system for all Landsat data is WGS 1984 UTM, and so all outputs are going to match that, and the geographic transformation used is only suitable for the lower 48 states. We'll get to this in a moment here. So then it prints the fields below were found in the unsupervised classification file, and then we create a list here, and even though there's not brackets here, when you use the list fields, this is a list, and then for field and unsupervised fields, it's going to print these out, and this is going to, the way it's formatted, will have them print in a row vertically instead of horizontally. And then we set the lookup field variable. And so this is the field that represents land cover classification that's in the classified image file. And that's the reason why we listed all these fields here, so they could see it and cut and paste it or type it out, because they need to enter it exactly as it appears, or again the tool would error. So then once they do that, confirm which field they chose and print it out, and then get the output projection from the classified image file by using the describe spatial reference. Also get the cell size from the classified image file by using describe mean cell width. So the next thing to do is get the parameters for the DEM. First, change the workspace to the DEM folder, then list all the files in that folder. Again, this is so it's easier for them to enter this information. Return it back to the original workspace, and then create a new list. This is going to hold all of the DEMs that they enter. Then we get the first DEM here using the raw input. Then we get the DEM cell size here, so that we can use this later. Then while DEMs is not equal to done, continue the loop. And so we print out that this DEM here was added to the DEM mosaic, and then we append it onto the list. And then it asks the question again, do you have any more DEMs to mosaic together? And this continues so that you can just keep entering as many DEMs as necessary for your study area. And then when you type done, it will exit the loop. So now we have a list, but the problem here is that these are separated by commas. But when you use these later in the Mosaic to New Raster tool, each raster needs to be separated by a semicolon. So this changes it, changes all those commas to semicolons in the list. Now we have all our DEM parameters. So we start getting the slope class parameters. And so the first slope class, we already know that it begins at 0, and then they enter the upper limit of that class. It confirms with them what they've entered. Same thing here. The second one, we already know what the bottom of the lowest value in that class is going to be, so we just have it print that out, what they entered here, slope class 1, and then they're going to set slope class 2 here, confirm with them what was what they've entered so far for the second class. Again, we know what the bottom of slope class 3 is going to be. They just need to enter the maximum. And then we know by default that the last class, class 4, we know it's going to be everything greater than whatever they entered for the maximum of slope class 3. So then we need to enter the cell size parameters that they want to use. So we got this information earlier using the describe. So the cell size of the unsupervised classification file is whatever they was in that file. So we know that for Landsat it's going to be 30 meters, but if they use a different sensor, it's going to print that out and confirm it with them. And then generally, we already know that it's almost always going to be in UTM, so it's going to be meters. This would probably, this would be incorrect if it was in feet, but nobody in science uses feet, so it should always be true. So then it gets the cell size, but this is in angular degrees here. So I add a note what this is going to be, because this hasn't been projected yet, so it's just going to print it in angular degrees. So I add this note down here, what this basically translates to in meters, but this is not going to be true unless they have a 1/3 arcsecond DEM. But that's like the most common, so I'd mention that, if it's in the video, I mentioned that if you have a different size, you need to look it up. So here we set the cell size variable using the user input, and so we went through this up here so they can make a good decision about what cell size to use. Confirm what cell size they've chosen. And finally, we've finished gathering up all the parameters and we can begin geoprocessing. And now we just basically have a string of tools, one after the other. So first thing to do is mosaic to new raster. We have our list that was all the DEM inputs separated by semicolons. We set the output file name, and then this is the Z value, which can remain at 1. Take all the defaults for everything else, and then set the mosaic variable for that output, and confirm with them that the file below has been created and print out the mosaic file path. Then we need to project the raster. And so I didn't want to do any projection up here because I want to use bilinear when projecting the DEMs for the interpolation method, and then that would require me going in and changing the workspace environment for other tools. But the project raster tool has a setting here for your interpolation method, so I felt that it was better to just do it here rather than keep changing the workspace or keep changing the environment setting for the default interpolation method. And then your input, the output projection, which we got earlier by using the describe, and the cell size that the user input earlier. And then here is the geographic transformation. So this is really important, and I had to do some research about how to enter this information and what would be appropriate to use. I didn't know really anything about it before. So if you don't need to use, this is optional as long as the output projection has the same datum as the input projection. But in this case, we want to change from the DEM's projection, which is in a datum of NAD 1983, to the datum that's used for the Landsat imagery, which is WGS 1984. So this tool works anywhere in the world, but right now it's set up just optimized for the lower 48 states. And so you can just Google about geographic transformations and you'll find this blog. This will be one of the first thing that comes up. And so it has, it says where, which transformation is suitable for which place. And most of these are all in North America. So all you need to do is basically see the number is different here. All you need to do is just change this number to use it at different places in North America right here. However, I assume if you get DEMs for other places in the world, they may have a different datum. So you need to like look up what that datum is, and then once you look in your file and determine what the datum is, then you can use this PDF that you'll easily find, and it has like every datum to whatever, WGS 1984 or whatever, and it says where it's suitable to use. So you'll just need to go through this list and determine which geographic transformation is appropriate. And this is a really long document, so be patient trying to look for it, but they're in here. And then by doing that, you can use this tool anywhere in the world. Alright, so then we set the projected variable, and then we're going to print out the path, confirm that this part of the tool is executed, and then we explain why we use bilinear interpolation here, so that they know that is what was used, and because the default would be nearest neighbor, but nearest neighbor is only appropriate for discrete data. In this case, we have continuous data for elevation, so that's why we've used bilinear. Okay, so the next step is to clip the DEM to the area of interest. So we're going to use the clip tool here, and the projected DEM is the file that we're going to use. It was the output from the last tool. Set the output file, and then this is the extent. So this is the extent of the classified image file, so this way they're going to match. And then over here, this is like what is going to happen if the boundary happens to fall in the middle of a pixel. Like, is it going to cut that pixel in half and resample it, or what's going to happen? So I read through it and decided this would be the best one to use, but you should note that this is sort of like the newer tool. There was another one before this that is still there that you can still use. It's called Mask, I believe, or Mask Raster. And so you can't change this. It's just, it has its default that they've determined is the best, but in this newer version you can change this, and this is going to give you slightly different values for your output. So that's something you could change and experiment with to see how it changes your results when you run the slope later. So then we set the DEM clip variable, and then we print that out, confirm that this part of the tool is run. And now we can use the clip DEM as a snap raster, and using a snap raster is a good idea because it's just going to ensure that all the outputs will have perfect cell alignment and all the cells will match up, and that's important when you start doing things with raster calculator and stacking files together when you mosaic them and stuff. And so this just changes the workspace environment, so everything after this is going to use this snap raster. So now we're going to create a slope file using the slope tool. So these are pretty simple. We use percent rise. We use the clip DEM as the input. This is the Z factor, which 1 is the default and 1 is fine, because our input and output are both in meters. Then we save the file, set the DEM slope variable, confirm that the slope tool is run with the user, and print out the file path. Okay, so now we need to generate 4 files, and these files represent our slope classes. And so this was one of the hardest parts, because using raster calculator, you use different expressions in Python than you would if you were just using it in the GUI. So this was kind of hard for me to figure out, but luckily I found a code example that was almost what I needed. So from there I was able to figure it out relatively easily. So here we're going to make slope class 1 file, and this is the raster calculator expression. So the DEM slope file, which was just generated, everything less than the maximum of class 1, and this variable was entered earlier by the user. And then set this variable here so we can use it later, and confirm with the user that the file was created. Then slope class 2, so then we just have a larger expression, so it's like so greater than slope 1, the maximum slope 1, and less than or equal to the maximum in slope class 2. And then again set this variable to use later, and print it out and confirm. Similar here, print it out, confirm. And then class 4, we know by default it's everything greater than the maximum slope class 3. So the next thing is to run the lookup tool, and here we're using for the input the classified image file, and the field that it's going to use to essentially as the dissolve field is going to be whatever the user input was back when we were collecting parameters. And then you'll see down here that the cell size was changed from whatever it was previously. In this case it would have been 30 meters with Landsat data, to whatever the user input was for their desired output cell size for all the files. And but you'll notice here that the syntax of this tool doesn't have a place for the cell size. So I just want to go back because I failed to mention that we changed the environment setting for output cell size, and we did that right here. Let's see, cell size right here at the beginning of the project tool. So I tried to use the global environmental setting here and have that work for every tool, and it did, except for the project raster. For whatever reason, this had no effect on the output, so I had to put it in here, and so it did have a place for that in the syntax. Maybe that's why it didn't have any effect. My other idea is maybe it's because this was in angular degrees. I'm really not sure why, but this did work. And so every other output though, this works, that the cell size has changed to 10 meters. Okay, so now we've done most of the geoprocessing tools. Everything left now is just basically raster calculator. And so this is the part I thought was going to be the most challenging. And it probably is, but I had done the other portion with raster calculator by the time I got to this. And, I had been working on this for a long time. So I was getting more comfortable with Python. So this actually went way better than I thought it would. So what you want to do is create the search cursor, and should note here that this is like, I guess I read that it was the older version of search cursor. The newer one is like arcpy.da.search cursor. And so when you enter the fields that it's going to be looking at, the syntax is slightly different. I tried to use the other one, but I couldn't figure it out. And I had no problem with this one, and it works fine. And then this here, row equals rows dot next. This is sort of like step to the next row is what this says. And then I create this class list. You'll kind of see why in a minute. So the value equals row dot value, and then you're going to append that value onto the list. And then so since we're in the while loop, this is just going to keep running over and over. And so here we use raster calculator, and this is we use the value variable that was set right here, and then our slope class 1 file. So whatever this is going to be like in the file I use, I have like 9 classes, I think it was. So in this case, the first time it goes through, it's going to be value 1 and slope class 1. This is going to be anywhere that these two things intersect. And the next one, we're still using the same value, value 1, and slope class 2, anywhere they intersect. So, this is a binary raster, so 1 is true. And also, as it's producing each file, we're adding a field. This is so in the next step, we're adding this class number field, as you recall, because the user needs to go back and change this to their number that they want for the final output file from this whole process. And so this basically continues, and then it gets to the end, and it's like rows.next, and then it starts over. And so when there's no more rows, it'll exit the loop with the rows.next. And then again, so the second time it would be like value 2, and then it'll go through and do the same thing again using value 2, and then value 3 all the way till 9, and then it'll be no more rows, and it'll exit the loop. And so this actually wasn't nearly as hard as I thought it would be. And also take note that all the outputs are following a stringent naming convention, which I also thought would really be hard, but I was basically just able to use like unsupervised, and then whatever the value was that we already got here, and then just add whatever the slope class is. And I already know, they're slope 1, 2, 3, and 4. And so that was really simple. And so we made this unsupervised class list just so we could get the output count, multiply it by 4, because for each item in this list, these were all the classes, we created 4 files each time. And then we can print that out and let the user know how many files were generated here. And then we tell them that all these files are in the raster calc outputs 1 folder. And then again, we use the search cursor here to get the value and the class name from the output from the lookup tool, and then it prints all that information out. This is because they're going to need this in the next step. That way they can conveniently copy and paste it into a Word doc. And in a similar fashion, print out all of the slope classes. And now they have all the information that they're going to need to run the next part of the tool. Then check in the spatial extension, and that's it. So now I'll explain the second part of the code, which is much shorter. Okay, so for the second part of the tool, again, we set our environment settings here, import ArcPy and Spatial Analyst, print out a little message, print out this. This is important. Make sure that you entered the class number for every file in the raster calculator outputs 1 folder. If you missed one, the tool will give you an error message to let you know which files are missing this information. So I felt it was really important to add this error message because it's so easy to accidentally miss one of the files when you're editing the class number field. So again, get the workspace from the user, and then create a list of all the rasters that are in the raster calc outputs 1 folder. And then we're going to also have another list. This is going to be the mosaic rasters list. That's going to be the input to the mosaic raster tool. So for raster in the rasters list, again, we use the search cursor with rows.next, so it's going to step through each row in every file. And we're going to be looking at the value field and the class number field. So we get the enter the while loop, and we get the value, and then we also get the output class variable by getting the information from the class number field for that row. And so if the value in that row is equal to 1 and the out class is not equal to 0, that means the user must have edited the file because the default is 0 for that column. So that means that they did not miss this file and they entered a new output class. So if that is true, then you're going to use raster calculator to multiply the 1 value by whatever that out class number is that they entered for their final output for that file, what they want it to be. And so then we save the file, and then here we set this variable for the raster output that we just raster calculator output that we just created, and then we append that to the mosaic rasters list. And so, but if the value is equal to 1 and the output class is equal to 0, then that means they must have missed it, and it prints out this error. And it's going to give them the name and path to that raster. And then it's going to go to the next row. And this is going to keep going, cycling through every file in the folder and then go through each row in that file. They're all binary rasters, so there's only 2 rows. Then after it's gone through all the files, then they've all been appended onto this list. And again, to use them as an input to the Mosaic the New Raster tool, we need to use the semicolon to separate them. And then we use the Mosaic to New Raster tool, and it's important here that you use the sum, and then that's it. The output is the final mosaic, and then we just use the add field to add the class name field. So then, as you remember, it'll be a text field, and you can go in there and edit it and add a name like Granite Mountains or so on. Then it prints out and confirms that the final mosaic file is in the process products folder. And if you're seeing any error message listed above, then you need to go into ArcMap, correct them, and run the tool again. And that's it. Hope you've enjoyed it. I know I have. Thank you for watching.